Okay, welcome back. In this lesson, it's lesson 15, we are going to study concavity or concave upward or concave downward. See this thing, when you have a rectilinear line, the equation of the rectilinear line is ax plus b. And if this is the equation, y of x, what is the first derivative? The first derivative is the derivative of ax is a, the derivative of b is 0. And what is the second derivative? The second derivative is 0. So what it means this? It means the rectilinear lines have a slope. The magnitude of the slope is a. And this slope, it never changes in the rectilinear line. It's always a. So the second derivative, the change in the slope is 0, because if the slope is always a, after some x, here the slope is a. Here the slope is a. So the change in the slope is 0. So when you have this kind of curve, like a rectilinear line, you say there is no curvature. So the curvature can happen because the function can do like this or can do like this. What is the difference between a function that does like this or does like this? This is concave upward, while this is concave downward. What is the difference? The difference is that the slope is growing up. Here the slope is bigger and bigger and bigger. And now the slope here is smaller, smaller, and smaller. So to see this, we can see like this. Imagine a curve that is concave upward. So let's say that the slope here is minus 10, minus 9, minus 8, 0, 1 positive, 2 positive, 3 positive, etc., or 10 positive. What happened to the slope? The slope is changing. It's changing when we walk from the left to the right. When we walk to the right, the slope is minus 10, minus 9, minus 8, 0, 1, 2. So the slope is changing. And the change in the slope respect to the x, this is the x, you are moving to the x. The changing in the slope is the changing in the slope, in the derivative of y respect to the x. So this is the second derivative of y respect to the x squared. And the changing in the slope is going up, is positive. You know, the changing is always adding 1 here, adding 1 or adding 8, add something positive. So when you have a concave upward graph functions, the second derivative of the function respect to the x squared is positive. The change in the slope are always positive. Meanwhile, when you have a concave downward function, the change in the slope, the second derivative of the function respect to the x squared, this is the x, so you are moving in this direction, and the slope is decreasing. The slope here, the slope is maybe plus 10, plus 9, is decreasing. 0, now 1, 2, and 3. So the slope is a change that is decreasing. Minus 1, minus 2, minus 3. So if you want this representation, it starts at 10, it goes to 9, it goes to 8, it goes to 0, and later on it goes to minus 1, minus 2, minus 3, etc. So the change in the slope respect to the x is negative. So the second derivative of the function is negative. So this is the only thing that we have to know about curvature. And let's go to do the problems. Now you can pay attention only to the first 3 or 4 problems of this lesson 14, and it will give you the idea how to solve the problems. Okay. Determine the open interval on which the function is concave upward or concave downward. The function is x squared minus x minus 2. What is the first derivative? 2x minus 1. What is the second derivative? Is 2. The second derivative is positive. So if it's positive, it becomes a concave upward function. The graph of the function is concave upward. So if f second of x is positive, it's concave upward. And it's concave upward in all the intervals from minus infinity to infinity. Let's go to the next problem. So determining the open interval on which this function is a polynomial is concave upward or concave downward. So we take the first derivative. We take the second derivative. The second derivative is 6 multiplied 1 minus x. When this is positive and this is negative, we'll say the interval where the function is concave upward or concave downward. In this case, this is positive when 1 minus x is positive, or when 1 is bigger than x, or when x is smaller than 1. So for x is smaller than 1, the second derivative is positive. So if it's positive, the curve will be concave upward for all x less than 1. And for x bigger than 1 will be concave downward. So in summary, for the interval minus infinity comma 1, the curve is concave upward. And for the interval 1 comma infinity is concave downward. And when x is equal to 1, what happens? F second of x is 0. F second of 1 is 0 when x equal 1. So there is a change in the concavity at x equal 1. And this point is named, the point x equal 1, is named as an inflection point. So x equal 1 is the inflection point, and is the point where the second derivative of x evaluated at the point x equal 1 is 0. Let's go to the next problem. Now we do problem 3. It's inside the open interval minus pi divided by 2 and pi divided by 2. What are the intervals where the function 2x minus tangent of x are concave upward or concave downward? Well, we do the same procedure. We find the second derivative of x, and we see what are the intervals where the second derivative of x are positive or negative. If we do the second derivative of x, you will find a minus, applying the chain rule, etc., you will find minus 2 tangent x secant square of x. So the question is when the second derivative of x is equal 0, and when it's positive and when it's negative. If it's 0, you have an inflection point. If it's positive, you have that the function is concave upward, and it's negative, you have that the function is concave downward. In this case, if you see this is the 0, this is where at x equals 0, f second of x is 0 because tangent of x is 0. So when x equals 0, so at 0 is an inflection point. The second derivative is 0. To the right of the 0, and between minus pi divided by 2 and 0, the second derivative is positive, you can plug in any number between minus pi divided by 2 and 0, like minus pi divided by 4. You plug in here, and you would see that in all this interval, the function is the second derivative. This second derivative is positive. And to the right, if you plug in, for example, x equal plus pi divided by 4, you will see that this function, the second derivative, is negative. So it's concave downward. So as a final result, the concavity is summarized like this. The function, the function f of x equal to x minus tangent of x is concave upward in the interval minus pi divided by 2 0. And is concave downward on the interval 0, pi divided by 2. So the procedure is always the same. Find the second derivative, find the inflection point, look at the right, look at the left. If it's positive to the right, so the concavity is concave upward. If it's negative to the left, the concavity is concave downward. And it's always the same. Okay. Well, in this case, it's opposite, as I said. At the right, the concavity is concave downward. At the left of the 0 of the inflection point, the concavity is concave upward. Okay, let's go to see the problem number 4. Now we change the function. The function is minus x to the 4 plus 24x squared. This is a polynomial. It's defined in all intervals from minus infinity to infinity, and we need to find the concavity of this function. So to find the concavity, we find the second derivative of the function. We make it equal 0. We find the inflection point, and we see to the right of the inflection points what is the second derivative. Is positive or negative? But in this case, this is an x squared. It has two solutions for the second derivative to be 0. F second of x can be factor like minus 12x squared minus 4, which this can be factored like minus 12x minus 2 multiplied by x plus 2. So the second derivative is 0 when x equal 2 or when x equal minus 2. So we have two possible points of inflection, and the 2 points of inflection is minus 2 here and 2 here. So we see to the left of minus 2. And we see that the second derivative, you plug in a number like minus 3, the second derivative is negative. So the function is concave downward. If you plug in a number between minus 2 and 2, like the 0, for example, you will see that when you plug in 0 here and 0 here, 0 plus 2 is 2, 0 minus 2 is negative. With this negative will be positive, so the second derivative will be positive, meaning that the function between minus 2 and 2, the function is concave upward because the second derivative is positive, and the same happens for the function in the interval 2, 4. On point 2, the second derivative is 0. On point minus 2, the second derivative is 0, is an inflection point. So these are the solution to this problem. Let's go to the next one. And of course, for this problem, you can use GeoGebra. You can graph the function x minus x to the 4 plus 24x squared. And if you plug in GeoGebra and you graph the function, you will see that these intervals are correct for the concavity. Okay, let's go to the next problem. Next problem says find all the points of inflection and discuss the concavity of the function x multiplied by x minus 4 cubed. What we have to do? The same. Find the second derivative, see in what interval they are positive, see when it's 0, see when it's negative. So if we find the second derivative, this is steps that I'm not going to say how to find because it's the product rule. and the power rule, mix it. So the second derivative with a little bit of algebra will be 12 multiplied by x minus 4 multiplied by x minus 2. So we have two inflection points. The point is x equal 4, x equal 2 here, and we have now three intervals to analyze the concavity. So if you go to the left of 2, let's say you plug in 0, you will see that the concavity is positive. The second derivative is positive. That means that the curve is concave upward. Between 0 and 4, inside 0 and 4, inside of the interval, the concavity, the second derivative is negative, meaning that the concavity is concave downward. And for numbers that are greater than 4, the concavity is upward. So as a summary, we have that the interval where the concavity is positive and negative is being summarized here in the interval minus infinity, comma 2. The second derivative is positive, so it means concave upward. In the interval 2, 4, the second derivative is negative, so it's concave downward. And the interval 4, infinity, the second derivative is positive, so it's concave upward. And the point of inflection are when the second derivative becomes 0, that is x equal 2 and x equal 4. If you plug in x equal 2 and x equal 4 on the second derivative, you will see that is 0. X equal 4, 4 minus 4 is 0, 0 multiplied by something is 0, or x equal 2, 2 minus 2 is 0, 0 multiplied by something will be 0. Okay, let's go to the next problem. So these are mechanical problems to do. The only mistake that you can do is finding the second derivative or analyzing in a wrong way the sign of the second derivative. Okay, let's go to do this problem. This problem says find the point of inflection. Find the point where the second derivative are 0 of the function sine of x plus cosine of x in the interval 0, 2 pi. How we will find the point of inflection? We find the second derivative. The second derivative is minus sine of x minus cosine of x. And how to find the point of inflection? The point of inflection happens to be when the function, the second derivative is 0. When the second derivative is 0, minus sine of x is equal cosine of x. Now, when this happens, when minus sine of x equal cosine of x, when the cosine of x has the same value as sine of x but negative. This happened to be in the fourth quadrant and in the second quadrant. And it happened to be when x equal 3 pi divided by 4 and 7 pi divided by 4. So this is 45 degree, here is a 45 degree, and here is also 45 degree, and here is also 45 degree. And at these angles, the sine and the cosine have a sign that is, when the sine is positive here, the sine is positive here, is negative here, sorry, and is positive here, the cosine. While at this angle, 3 pi divided by 4, the sine is positive and the cosine is negative. And they have the same value when the angle is 45 degree or a multiple of 45 degree, like 3 pi divided by 4 or 7 pi divided by 4. So now the problem is almost done. We found the inflection point. The inflection point are 3 pi divided by 4 and 7 pi divided by 4. And we see on each interval what is the sign of the second derivative. If we plug in a number between 0 and 2 pi, 3 pi divided by 4 is a point of inflection, 7 pi divided by 4 is another point of inflection. We see to the right, maybe we plug in pi divided by 2. If we plug in pi divided by 2 in the second derivative, we would see in the second derivative, here is the second derivative, minus sine of x minus cosine of x, you will see that for any number, any angle, any point that you put, that you substitute on the second derivative, it will be negative. At this point will be 0, and for any point that you put, like 5 pi divided by 4 maybe, the concavity, the second derivative, is positive, means that the curve is concave upward. And if you put a number, if you insert a number between 7 pi divided by 2 and 2 pi, at 7 pi divided by 4, there is a point of inflection and the second derivative is 0. But if you plug in a number between 7 pi divided by 4 and 2 pi, the concavity is negative, meaning that is a concave downward. So the conclusion are written here, and this is what I have said. The two point on inflection are 3 pi divided by 2 and 7 pi divided by 4. On this interval 0, 3 pi divided by 4, the concavity is downward. In the intermediate interval 3 pi divided by 4 to 7 pi divided by 4, the concavity is positive, so it's upward. Is concave upward, on this interval is concave downward, and the problem is solved. The point of inflection at 3 pi divided by 4, 0, because if you plug in the original function is this one, cosine of x minus sine of x. If you plug in the inflection point 3 pi divided by 4, if you plug in at this, the function f prime is 0. And if you plug in 7 pi divided by 4, the y of the function is 0, so the 2 points of inflection are here. These are the 2 points of inflection. Okay, let's go to the next problem. The next problem say more of the same. You can stop here and not do any more problems because this is more practice, but if you want to see and to practice more, here is another problem. And the problem say you have a polynomial that is continuous and differentiable everywhere, and it say use the second derivative test where applicable. So we found the second derivative, we find the point of inflection, and we see at each side of the point of inflection. So we find the second derivative. The second derivative is 6x minus 6, or 6 multiplied by x minus 1. So the point of inflection is x equal 1. So at this point, x equal 1, there is a point of inflection when the second derivative is 0. What happened to the right of x equal 1 and what happened to the left of x equal 1 is what we are interested to know the concavity. The result for this problem is that to the left of the inflection point, x equal 1, this is the inflection point, to the legs, the concavity is negative. For example, if you plug in the 0 that is to the left of x equal 1, the concavity is negative. The second derivative is negative, it means that it's concave downward. So at x equals 0 is a relative maximum. Why? Why is at x equals 0 a relative maximum? Because if you go to the first derivative is 3x multiplied by x minus 2. When x equals 0, f prime of x is 0. When x equals 0, f prime of 0 is 0, because 0 multiplied by minus 2 is 0, so it's a local maximum. Then the conclusion are written here. The conclusion is that for the function x cubed minus 3x squared plus 3, the point 0,3 is a relative maximum. The point x equal 2 is a relative minimum. And the point 1,1 is an inflection point. And to the right of the point x equal 1, the concavity is, when you plug in the 0, the second derivative is negative, 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 and here is positive, positive, positive. So the concavity is concave upward or concave downward, depending on the interval. On the interval minus infinity comma 1 is concave downward, and on the interval 1 comma infinity is concave downward. Okay, this is the problem. Let's go to the next one. The next one is the same that all the others. You can see the calculation here for the function x plus 4 divided by x. I leave you to see all the calculation and what is written here. And the summary is here. So the summary is here. The conclusion are here. X equal to is a minimum, local minimum. X equal minus 2 is also a local minimum. And the interval where the function is concave upward and concave downward, the interval are here. You can find the interval because the second derivative is positive when x is positive and is negative when x is negative. So is concave downward on the interval 0, infinity, and is concave upward on the interval minus infinity, 0. That's all. Well, and at 0, the second derivative doesn't exist. Also, the first derivative doesn't exist. At x equals 0, also the function at x equals 0 doesn't exist, the value of the function. So we don't wonder, we don't ask ourselves what happened at x equals 0 because the function is not defined at x equals 0. Okay, this is problem 9. You see it, how it is being solved. It's not difficult to follow the calculations. Here is the summary. To the right of the 0 is negative, second derivative is negative. To the left of the 0 is second derivative is negative. To the right of the 0, the second derivative is positive, meaning that the curve is concave upward. But I made a mistake here, so let me change the mistake. Let me erase here. And here the concavity is positive here and negative here. If you plug in a number, it's like this. Okay, so the summary is here. This is the curve, and this is the second derivative. This is concave upward, concave downward from 0 to infinity. At the point x equals 0, the slope doesn't exist. It's an infinity slope, it's a vertical line. And if you see here, when you plug in x equals 0, the slope doesn't exist. And the last problem, you see also how it's being solved is discuss the concavity of the function x to the 2/3. The function x to the 2/3 does like this. What happened at x equals 0? What is the slope at x equals 0? Well, g prime of x is 2/3 x minus 1/3, or it can be written like 2/3 1 divided by a cubic root of x. When x equals 0, this doesn't exist. The slope is infinity. It doesn't have a slope here at this point. So x equals 0 is a critical point of this function, and the second derivative happened to be minus 1/3 1 divided by cubic root of x to the 4. So the second derivative is negative on the interval minus infinity 0, and is positive, and is also negative on the interval. Let me see. On the interval, let's say that you plug in the number minus 2. Minus 2 would be a positive number, so this would be it would be negative. And also, if I plug in x equal 2, it will be a positive, so this will be a negative number. So it's a concave downward and concave downward also. So it's always concave downward. And at x equals 0, the second derivative is not defined. And also at x equals 0, the first derivative, the slope is not defined. But the function at x equals 0 is defined to be 0. Okay, that's all the 10 problems that you have to do. There are some problems that you can practice from your textbook, like this one. They are very similar. I'm not going to do it. This one, you can do it. Or this one, very easy to do it. To find the relative extrema in inflection. This is for lesson relative extrema for lesson 14. You find the critical points when the first derivative is 0. And this is the problem. Okay, and put it one. This problem also you can do it. Let's go to erase this one. Okay, and this is the problem. Okay, and this problem you can find also, but they are very, very similar. The same criteria, and maybe you can do this problem. This problem is sketch the graph of the function that has the following property. So the first thing to do this kind of problem is to put a line where you define who is f prime of x and what is f second of x. So if you put a line, the information is here. It would be like this. It say the problem say that you should sketch the graph of a function that has the following property, a, b, c, and d. A say that the first derivative, the e, is positive. It means that the function is increasing on the interval for x smaller than 1. So for x smaller than 1, the function is increasing. And for x bigger than 3, the function is also increasing for x bigger than 3. So this is the information for f prime of x. The other interval is between -1 and 3. Between -1 and 3, let's go to put this line here to separate the intervals. And between -1 and 3, the slope is negative, so the function go down. It has a negative slope. Now it says that for x smaller than 2, so let's go to put it here. For x smaller than 2, in this color, for x smaller than 2, f second of x is negative. This means that the concavity is concave downward. And for x bigger than 2, the concavity is concave upward, because f second of x is positive. F second of x is positive. So how you will graph the function? You see that here in the interval, when x equal -1, the function is increasing, and at x equal -1 to the right is decreasing. So x equal -1 is a local maximum. Also, we see that at x equal 3, here to the left the function is decreasing, and now to the right of the 3 the function is decreasing. So at x equal 3 it has a minimum. So let me erase here, and the function will do like this. And x equal 3 will have a minimum. So we have located the minimum at x equal 3, the maximum at x equal 1, and the curve is concave downward in the interval -infinity to 2. So here is the point of inflection. At x equal 2 is the point of inflection. So the function will do like this. Here at x equal 2, it changed the concavity, and the minimum is at x equal 3. And the maximum is at x equal 1, minus 1, sorry. So placing the information like this, you can more or less sketch the function. Here you can sketch this function. I have done it here. You check the intervals of f prime of x, f second of x, and you see if it makes sense for you, this kind of sketch for the function. I'll see you soon. Good luck.